Today we are going to learn the Bernoulli equation so we can understand how the pressure varies in this pipe. You can see that this pipe has varying cross-section, and that means that we'll have some change in velocity from V1 to V2. You can also see in this pipe we have some change in height, and you'll also see I have a potential energy term. So the point is we need an equation that can understand all of the variables we have at play, and perhaps our goal for today is to find P2, the pressure at the final position. In order to do this, we need to use the conservation of energy, which, as you know, means the energy at position 1 equals the energy at position 2. We know that energy is the ability for something to do work. So as a fluid flows through this pipe, it has some pressure and has some volume. So the pressure times the volume is the amount of work that the fluid does on the walls of this pipe. Second, we know that the fluid has some kinetic energy from its velocity, and that's 1/2 mv squared. And finally, we know that the fluid could have some potential energy from its height. And we have a change in height here. So we have three terms, PV, kinetic energy, and potential energy. So our energy at position 1 is equal to the pressure at position 1 times the volume plus, and for both of these mass terms, I'm going to replace them with rho v. And you'll see why I have done that in a second. So we have rho volume, don't get these two v's confused, and this is velocity squared plus rho volume g h1. So we have h1, we have v1 there, and then our energy at position 2 is pretty much the same equation, except we're going to use our variables from the second position. So keeping rho v in place of mass, and that's 2. So what Bernoulli did was cross out, he canceled out the volume terms because they're in every single term, so he could divide it out of that, of each of those equations, and that simplifies everything to a pretty nice balance. So we have on one side E1, on the other side E2 in order to show the conservation of energy, and that's P1 plus 1/2 rho velocity 1 squared, and that's our potential energy term, plus rho g h1, and that's our kinetic energy term, that's our potential energy term, and then the same for the second side. So our P2, which is what we would be looking for in this problem, 1/2 rho v2 squared plus rho g h2. So like I said, this is our kinetic energy term. This is our potential energy term. And if we had all of these variables except for P2, and we knew which liquid we were dealing with, thus we could know its density, we would be able to solve for P2. So this is the Bernoulli equation.